It's actually possible for a car to turn on a banked curve without friction if the speed of the car and the angle of the bank are just right. This is a terrific physics application for folks who live in icy areas. Especially when the roads freeze over, they try and design the banks at angles so that the cars don't need a whole lot of friction. Let's determine the required speed of the car for a given bank angle. So I'm going to start off by drawing my banked angle, and on here we'll put our car. I'm going to look at it from behind again. There's the license plate. And we have some angle theta to our incline. So we're going to start off with our free body diagram. Now, even though the car is on a banked angle, because it's turning in a circle, that means that the motion of the car, the acceleration, is toward the center of the circle. That way, we're not going to tilt our axis. We're going to keep the acceleration going straight toward the center of the circle. So when we draw our free body diagram in this case, I'm going to put my y-axis, my x-axis. Here's the car. We, of course, have mg down, its weight, and the normal force. But the normal force is here at an angle, and that angle there is theta. So when we draw our pseudo-free body diagram, now we've got to break up the normal force into components. There's my x, there's my y. We still have mg down. Now, if we want the x component of the normal force, that's going to be the opposite side of this triangle. So the x component here is going to be Fn, opposite side, sine theta, and the y component, again, is going to be the adjacent side, Fn cos theta. So once I have that, my pseudo-free body diagram, I can come back here and I can write my Newton's second law equation. F net c equals, well, I'm going to replace F net c with all of the different forces I have pointing toward the center of the circle. In that case, it's Fn sine theta. So Fn sine theta points toward the center of the circle, and I know that must be equal to mv squared over r. All right. Let's do my F net y equation over here. Net force in the y direction is going to be Fn cos theta minus mg. And all of that must equal 0 because the car is not going to spontaneously go flying up off the bank or down into it. Not in the situation here where we're saying that it's just right that it's going to stay on the banked curve. So I can say that normal force, cosine theta, must equal mg, or the normal force equals mg over the cosine of theta. Now let's go back over here. With that information, knowing that Fn equals mg over cos theta, I'm going to replace normal force here with mg over cos theta. So I have mg over cos theta. I still have the sine of theta here, times the sine of theta, and all of that equals mv squared over r. Can do a simplification here, divide both sides by m. And by the way, sine theta over cosine theta, that's the tangent function. So therefore, g times the tangent of theta equals v squared over r. Or, to solve for the velocity, v squared equals gr tangent of theta. Or to get v by itself, take the square root. V equals the square root of gr tangent of theta. I don't need any friction whatsoever when I have the situation where the velocity is equal to the acceleration due to gravity times the radius of the curve times the tangent of the bank angle of the curve, square root. Hope that gets you a good start on centripetal force and centripetal acceleration. Thanks for watching Educator.com, and make it a great day.